It's time to talk about Hermitian and symmetric matrices. In many ways, these are sort of the dual of the unitary and orthogonal matrices. I'm going to talk about Hermitian matrices, namely those complex matrices for which A star is equal to A. Remember, by A star we mean A transpose conjugate. And over the reals, this is saying that A transpose equals A. However, we'll stick with this definition since it applies to both real and complex matrices. The key idea behind a Hermitian or symmetric matrix, and the things that makes them so useful, is that they are tied to the idea of an inner product. Recall that we can define an inner product, V star W, which is the Hermitian inner product, which corresponds to the dot product over the real numbers. Often we'll write this as angle bracket VW. This is a very common notation, say, in physics and some forms of geometry. So, first of all, based on this definition, you can see an immediate property. So this is the key property. Is that if I take a matrix A and I apply it to W, and I take the inner product with V, well, I can write that this way. And using the contravariant nature of star, we have this. So in other words, VAW is AVW. So the key thing about a Hermitian matrix, or again in the real case a symmetric matrix, is that it can move across the two sides of an inner product. If you apply A to W or apply A to V, either way is the same thing. Now exercise 2.3 in Trefethen and Bow has some very important consequences. It seems like a fairly minor exercise, but in fact this is one of the key facts that makes all of geometry work. In fact, in a broad sense, it makes the universe itself work in the sense that we understand how general relativity behaves. We'll come to that later. For the moment, the idea is that we have a Hermitian matrix. And this implies two facts. First, that all eigenvalues of A are real. Now that's quite surprising actually, right? Because if you have a complex matrix, its eigenvalues can be complex. In fact, for a real matrix, its eigenvalues can be complex. Say a rotation matrix. But if you have a Hermitian matrix, even if it's a complex Hermitian matrix, its eigenvalues are always real. Moreover, A has a basis of eigenvectors. And thirdly, those eigenvectors are all orthogonal. If you combine these three facts, we have what's called the spectral theorem. This is a key theorem in linear algebra. It's one of, I think, probably 3 or 4 theorems that really make all of geometry work in the sense of differential geometry. So I'd put those as, say, the fundamental lemma of linear algebra, which is that you have the rank nullity theorem, you have Jordan canonical form, and you have the spectral theorem. And those 3 things basically make all of the geometry of linear systems work. Now, the spectral theorem is often phrased in the following way. If A is Hermitian, then there exists, let's call it U in UN, a unitary matrix, such that A can be diagonalized by a unitary matrix to a real diagonal matrix. Over the real numbers, this is true for the transpose. So if A is symmetric and U is orthogonal,